Kubernetes and GKE Part 40. This episode has 2 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Explain Cilium. Here's a strong way to approach it. Cilium is a modern networking, security, and observability solution for Kubernetes that uses EBF in the Linux kernel to provide high-performance pod networking, advanced security policies, and deep visibility into network traffic. It is also a container network interface plugin. Core idea: Cilium replaces traditional networking layers with EBF-based intelligence inside the Linux kernel, making Kubernetes networking faster, more secure, and highly observable. Why Cilium is used: it helps to provide high-performance pod networking, enforce advanced network security policies, replace actionable-based networking, offer deep observability, L3, L7 visibility, support service mesh capabilities. In some setups, key technology, EBF. Cilium is built on EBF, Extended Berkeley Packet Filter, which allows running code directly in the Linux kernel, fast packet processing without context switching, advanced traffic filtering and tracing. How Cilium works: traditional networking, actionables-based, uses actionables rules, slower at scale, hard to debug. Cilium networking, EBF-based, pod EBF program in kernel, direct routing, destination pod, no heavy packet rewriting, kernel level decision making, high performance. Key features of Cilium: 1. Pod networking, CNI, assigns IPs to pods, handles routing between nodes. 2. Network security policies, Kubernetes network policies, enhanced, L7 policies, HTTPG, RPC, Kafka, filtering. 3. Observability, Hubble. Cilium provides Hubble, which gives real-time network flow visibility, service dependency maps, security insights. 4. Service connectivity, replaces Kubeproxy in many setups, direct service load balancing using EBF architecture. Overview: pods, EBF kernel layer, Cilium agent, Kubernetes API, network routing. Cilium versus traditional CNI, Calico or Flannel. Feature: Cilium traditional CNI's technology, EBF actionables or VXLAN, performance very high, medium observability, built-in Hubble, limited security. L3, L7 policies, mostly L3, L4 complexity, moderate. Simple analogy: think of Kubernetes cluster equals smart city, traditional CNIs equals traffic police using manual rules. Cilium equals AI-powered traffic system inside roads that instantly decides best routes and enforces rules in real time. Where Cilium is used: large-scale Kubernetes clusters, cloud-native microservices, security-sensitive environments, high-performance networking systems, service mesh replacements or enhancements. Benefits: extremely high performance, kernel-level processing, advanced security policies, L7 awareness, deep observability via Hubble, replaces Kubeproxy in many deployments, reduces networking overhead limitations, requires modern Linux kernels. EBF support, more complex to operate than simpler CNI, steeper learning curve, debugging kernel level issues can be challenging. Cilium versus Calico. Feature: Cilium Calico core tech, EBF BGP or actionables, performance higher, high L7 policies, yes, limited observability, strong Hubble, basic complexity higher, medium interview ready. Definition: Cilium is a Kubernetes CNI plugin and cloud-native networking solution that uses EBF in the Linux kernel to provide high-performance pod networking, advanced L3, L7 security policies, and deep observability, enabling efficient and secure communication between services in modern Kubernetes clusters. Nice. Let's continue. Question 2. What are common Kubernetes failures? Here's a strong way to approach it. In Kubernetes, failures usually come from a few predictable areas: cluster components, networking, scheduling, storage, and application misconfigurations. Below are the most common Kubernetes failures. Interview focused. 1. Pod not starting, pending state. Cause: no available CPU or memory node selectors or affinity mismatch. Taints not tolerated. Cluster autoscaler not scaling. Symptom: pod stays in pending. 2. Crash loop back off. Cause: application crashes on startup, missing config or env variables, bad command or entry point dependency, service unavailable. Symptom: pod keeps restarting repeatedly. 3. Image pull back off or error image pull. Cause: wrong image name or tag, private registry auth failure, network issue to registry. Symptom: failed to pull image. 4. Boom killed, out of memory. Cause: container exceeds memory limit, no proper resource tuning. Symptom: pod restarts unexpectedly. 5. Node not ready. Cause: Kubelet down network failure, disk pressure or memory pressure, runtime issues impact. Pods rescheduled elsewhere. 6. Service not reachable cause. Wrong selector in service endpoint not registered. Kuba proxy issue, network policy blocking traffic. 7. DNS resolution failure cause. Core DNS pods down, misconfigured DNS policy, network issues between pods and DNS result. Services not reachable by name. 8. Network policy blocking traffic cause. Over-restrictive network policy, missing ingress or egress rules symptom. Pod can't communicate with other services. 9. Crash due to liveness probe failure cause. Wrong probe configuration, app slow startup, dependency delay result. Kubernetes keeps restarting pod. 10. API server issues cause. ETP overload, high API request volume, control plane failure impact. Kubectl commands fail or slow. 11. ETP failure. Critical. Cause. Disk full corruption, network partition impact. Cluster becomes unstable or read-only. 12. Scheduling failures cause. No matching node resources, affinity or anti-affinity conflict, resource quota limit symptom. 0 or 3 nodes are available. 13. Persistent volume. PV issues cause. PVC not bound storage class, misconfigured cloud volume provisioning failure. 14. Config map or secret issues cause. Missing keys, wrong mount paths, incorrect environment injection. 15. HPA not scaling cause. Metric server not installed, wrong CPU threshold, missing resource request, simple classification, control plane failures. ETP issues, API server overload, node level failures. Kubelet down, node not ready, application level failures. Crash loop back off, killed, networking failures. DNS issues, service unreachable, network policies, storage failures. PVC or PV binding issues. Simple analogy, think of Kubernetes as a city. Nodes equals buildings, pods equals rooms, failures equals electricity issues. Broken elevators, blocked roads, missing addresses, interview ready definition. Common Kubernetes failures include pod scheduling issues, image pool errors, crash loop back off, killed containers, node not ready states, DNS resolution failures, service connectivity issues, storage binding problems, and control plane failures, all of which typically arise from resource constraints, misconfigurations, networking issues, or underlying infrastructure problems. Great, moving on. That wraps up this episode. Nice work practicing, and see you in the next one.